If you understand football, that's hilarious. However, not everyone understands football.
Dasher would have worked too. Yeah. But I think Blitzen's a little bit sweeter. But whatever. So this is what I brushed past yesterday, and it, like I said, it really caught me off guard. What we're gonna do is first off restrict the domain. And the good thing about this is it's in vertex form. Can anyone right now just quickly tell me where the vertex of this parabola would be?
5, 5, 8, or
Just 5, 3. Good job, guys. And so the thing about what makes this method nice is that if we know, bless you, if we know where the vertex is like right away, bam, then we can know where to restrict the domain right away. So unlike the other one that we're going to do after this, we don't have to stress about that whole negative b over 2a finding the vertex, because vertex form literally just spits it out and gives it to you. So what would the domain restriction be on this one?
3.
It's going to be the set of all x's such that x is greater than or equal to 5. It's the horizontal that we're interested in. Okay, so because the vertex, let me make a quick sketch here. So because the vertex is at 5, 3, the point 5, 3 would be, so like here's 1, 2, 3, 4, 5, and the 3 honestly doesn't matter, but here's the vertex right here. So we know now that this is a parabola whose shape is something like this. Are you with me? But again, knowing the horizontal nature of that vertex, knowing that the x point, the x value of the vertex is at 5, tells us horizontally where to go snip, snip, and chop off the graph. Okay. Did you have you good? I'm sorry, I thought I saw. So any questions about just that? So when we see one that's in vertex form like this, the one that's written with the parentheses squared, whatever, that's happy day. Very little work to have to do. So the other side of it was the side that I just very casually brushed past, and apologies in hindsight for that. We have to find the inverse. So this is a thing. This is sort of an easier version of what we have to do next. What the first thing we're going to do is we're going to swap, and to find an inverse, always the first step is to switch y with x, and then switch x with y. So what's nice about this is sort of comically when we do the other problem, I hope you leave today feeling better about this than I left you yesterday. I feel bad about that. This is going to be a step along the way when we do the harder ones. This is what we achieve to get to. So what would be our first step here? Get rid of the 3. Good instincts, right? We know we can't go down like exponent root road if we have that straggler 3. So we're going to move the 3 to the other side, and we're going to have x minus 3. Like this. Okay. So you always want to make sure, as always been the case with anything like this, that you isolate any sort of root or exponenty kind of thing, because the other, we don't want to go down that road, like I said, with extras. What's the next thing? And remember, when we square root, we're just going to keep the principal, the positive square root. So generally, I would just side note here, remember from the olden days, if I had like m squared equals 16, the answer is not m equals 4. Do you remember what the answer is? It's positive or negative 4. So just always remember that when you're square rooting, technically you're supposed to consider both sides of the coin, the positive and the negative, but we just want to keep the principal one, the positive one. So the way it's going to look when we're done square rooting is we're going to get the square root of x minus 3 equals y minus 5. Right. And then we're done. So I feel like this is the significantly simpler version of what we're going to do next. And so, yes, if I move the 5 across, and the function I called f of x, so his inverse I will call f inverse of x, and it will be the square root of x minus 3 plus 5. Do you have any questions just about that? Okay. I don't intend to do another one just like that unless you want to. I'll come back to it. But more what I want to do is the harder version because I just blew right past completing the square. And in my defense, we did do it in Algebra 2, but still kind of rude of me to assume that it would be fresh in your mind. So let's try one of those. So let's come up with another function like g of x. And let's have him be we'll keep this as simple as we can. So like let's do x squared plus 4x minus 6. So way more work this time when we want to restrict the domain because the vertex doesn't just fall out and land in our laps, right? So can you guys remind me from yesterday and from a long time ago, how do we start finding the vertex?
X would equal negative b over 2.
Right. Good. And so this is where we got to bust out our cast of characters. We don't need A and B when it's already in vertex form, for God's sake. But A is obviously 1. It's in front of x squared. And B is obviously 4. And C is of no concern, right? So when we go to work out negative B over 2A, that's like our magic formula right there. What's that going to look like for us?
Negative 4 over 2.
Negative 4 over 2 times 1, which is 2. And what does that mean? Right. And so the answer to the vertex is negative 2 comma something. And the something, as I said in the last example, is inconsequential. Don't care. Could be anything at once. So where does the domain restriction happen? At negative 2. That's the horizontal nature of the vertex. That's where it is centered. That's what I care about. So we're going to hit it with the old snip. And again, we're just going to say that the domain then will be declared to be the set of all x's such that x is at least negative 2. So just knowing this number here is the key, right? That's the memo. Still good? Okay. Let's go and then find the inverse now. So we've done our domain restriction. I'm going to erase it because I'm recording. I can do stuff like that. So now we're going to do the old swappy doppy. So let's first start by switching. Let's call this y and x, and let's call this these x's over here y's. And I really, if 6 of you can do this, that's great, but I'm a failure. We're a failure as a team if only 6 of us can do this. It's imperative that we all speak up if we don't know. What is the first thing we do?
Negative 6 for the sign.
Yes, we're going to move the -6 out of the way. What we're doing is we're clearing a landing strip right now for something called completing the square. We want this problem to look like the first problem, right? So that we can square root. We can't square root something like this though, because it's not a square. We're going to make it a square, hence the name. So we're going to take the 6 and we're going to move it off to the side like this. Okay, clear a little space. Thank you. Okay. Say it again. Do you want me to add?
No, it's not important.
It is. So this is where, thank God, we're allowed to use notes. This is where you just have the algorithm written down. Let's just do this, then this, then this. The next thing you do is you take the number in the middle, the artist formerly known as B, and you take half of it. And half of 4 is 2. And then you square it, and that is 4. And because you get 4, 4 is the magic number that you put there. Understand that that 4 becomes part of this package product. Those 3 terms now travel as a packaged product. They will all collectively combine into something looking different here in a moment. And how do we erase our footprints? We turn around and subtract, which is such a crazy thing. Like we do one thing and undo it somewhere else. But we want the evidence to look like we were never here. The net result of +4 -4 is nothing, no change. So when you take the underlined red thing and factor it, what does it become?
Y plus 2 squared.
Yeah, and again, you would speak up at this point if you didn't know how we were doing that, right? So we have x equals y plus 2 times y plus 2 squared. Yeah, that's how we write it. And then what's the result of that? And you would realize at this point now that this kind of looks like something that we saw earlier, right? It's in that vertexy sort of form. In fact, you could even go this far before you change the variables. I don't know if anyone was ever going to ask that question, but you could have left all the y's and x's as they were. And this could now say y equals the quantity of x plus 2 squared minus 10, and then you could swap them at this point, and it would be just fine. Okay, yes.
Would you, when you convert it back to vertex form, would you not want people then to find the domain? Or restrict the domain, since you can use that now to restrict it, since it'd be the same.
Well, it's an interesting sort of proposition. You have to restrict the domain of either the function or its inverse, right? I don't know if I'm answering your question correctly. I don't need to restrict the domain of this one, other than to say that when I'm square rooting, I just take the principal square root. So I'm not so much restricting anything here as I am just keeping one. I'm not going to answer your question correctly. Let's work through and see if you could try your question again, and I'll see if I can make sense of it. But no need to restrict anything right now. We've already restricted before, right?
I'll explain it.
Okay. We'll try again. Round 2. Anyways, we're back to where we started class. What do we do now? Add 10. Good. So we're ready. So we're going to have x plus 10 on the left-hand side. And on the right-hand side, we've still got our square. And what do we do next? Square root it. So we're going to have the square root of x plus 10. And that's where we could have a case to put positive, negative, but we don't want to. We only want the principal version, the positive one. And that's equal to y plus 2. Last step. Good. So we have g inverse of x is going to equal the square root of x plus 10 minus 2. Got it? Does that, I don't know, maybe I misread the room, but I felt yesterday like that was a bold thing to just go through so fast. Do you feel like it's easy? You got it? Okay. So if you're interested, I'll just show you this in the recording. I was playing around on Desmos yesterday, and this is something that you can do too. Desmos, I mean, your calculators are pretty rad, but Desmos is pretty rad too. But one of the problems in particular, so like let's take the one we just did, for example. So the one we just did, the original function was x squared plus 4x minus 6. I just want to show you how to do this on Desmos. So we go x squared plus 4x minus 6. And I'm going to get rid of these other graphs here. So there. So you see that what we have here is a parabola predictably, and we know where the vertex is going to be. You can zoom in on it and see that the vertex is at -2, just like we said. So right now, if I were to try to invert this, its inverse wouldn't be a function, correct? Because this fails the horizontal line test. So the inverse of this, we just did. You guys, looking at your notes, can you tell me what the inverse of this was? It was the square root of something. X plus 10 and then minus 2. So if I zoom out on this, do you see how it's currently, those are not inverses. You can clearly see that the red graph and the black graph are not mirror reflections of each other, right? But I wanted to show you what happens if we clip half of it off. And to do this in Desmos, if you ever want to play around with it, all you have to do is go after the graph and put a curly bracket and say what you want it to be. So it'll go away while it's waiting for you to say. But remember, we want to keep all the x's that are greater than or equal to -2, I believe is what it was. And then it comes back to life. And you can see that's how easy it is to restrict a domain when you're just screwing around on the computer. You can learn a lot from just playing on your calculator or playing on Desmos. And so I just wanted you to see that that's the language that you would use. But just I was playing around after you guys left yesterday, and I just wanted you to see that, if nothing else, they look pretty cool, right? But you can clearly see now that they are inverses of each other. So good. Are you ready to press on to one of the word questions? Okay, let's get to it. Let's hit up problem 9 first. Problem 8, we've been down that road. You did 3 or 4 assignments on that, so I'm not too stressed about number 8. Just number 9. And number 9, actually, you know how to do also. So Number 9's a word problem that we don't have to think of as a word problem. I think it was written. Would like to say again that I had nothing to do with the creation of this district assessment. It was when a time when I wasn't in this class, I wasn't part of that group of people. So when they wrote this question, I assume they just wanted it to be another word problem. So really, at the end of the day, it's just a math problem. So in part A, before part A, we have an equation that says 0.24 e to the power of 5x equals 12. And then the part A goes on to say to solve the equation. Note that after that, it says your solution has to be expressed as a base E logarithm expression. So we don't want in part A to get some answer like 1.235 or something like that. So let's just talk mechanics. We've done this. You know what to do. In fact, I think I gave you a whole assignment on this. What would we do first? Absolutely not.
You'd divide by two.
Correct. The golden rule when working with exponents and radicals is that there is no funny business until the part that is the exponent or the radical is by itself. So we have to divide both sides by 0.24 like this. That's just a sort of a universal take it with you kind of rule when working with exponents, logs, roots. So we're left with our goal, like mission 1 accomplished. We got e to the 5x by itself, and it just happens conveniently that 12 divided by 24% is exactly 50. Okay. Calculator does all that for you. Now I'm ready. Coop, what are we going to do now? Now we're going to natural log both sides, correct? And we know to use a natural log because there's an e, and we really want that e to, we want less stuff to have to deal with when we're done. So we're going to drop the 5x, and it's going to be multiplied by the natural log of e, which is invisible as far as I'm concerned. And then the right side is going to be the natural log of 50. And what's the last step? Divide by 5. So the answer to part A on this, and I can give you more of these, don't worry if you want, but the answer to part A is that x equals the natural log of 50 all divided by 5. Note that it's not 50 divided by 5, 10. It's the natural log of 50 divided by 5. So this is what we or they, whoever wrote this test, whatever standard it was based on, this is what part A needs to look like. That's a base E logarithm expression. And what do the instructions say to do in part B? Evaluate it. Right. So this is where we plug it in. Anytime someone says evaluate something, they're like, give me an answer. So, I mean, the natural log of 50 divided by 5, that doesn't mean anything to most people, including myself. Like I'd have to sit here and think about what it is. I don't even know what it is. So we type it into our calculator, hit enter, and I'll let you guys do that, or I can just tell you what it is. That's up to you. It's good practice. Make sure you use the LN button. Also, make sure that you close the parentheses after the 50 before you hit divided by 5. I'm starting to hear the number trickle out. So we should change our equal sign to the squiggly equal sign and say x is approximately equal to 0.782. I'm just following directions. It says to round to the nearest thousandth, and thousandths places is the third decimal point. So is that something we can all be comfortable with? Okay. So that looks like a word problem, and honestly, at the end of the day, it's really not. The next one is straight up a lot of words. It's a very scary problem until it's not. And I don't know how to approach this. I feel like, I mean, there's lots of examples of compositions in the real world, but this is an example of a real time, like real world sort of application of a composition. So it's a very interesting problem. Like I said, I did modify it. So I'm talking to my buddy over in Pine right now about modifying the actual test, because the test as written is, I think, a little bit wonky. So the way I have it, and I just had to get creative with this, is that there's oil spilling from an offshore rig, but somehow like maybe the tear in the pipe is getting worse or something like that. And every day the amount of oil being spilled is increasing. Do you guys agree that to continue to have the radius of the oil spill circle increasing by the same amount, we would need more oil each day? Again, you don't just have to nod to be polite, but I hope you're buying what I'm selling there. That for me, like if I in day one, if the radius of the oil spill is 3 miles, so after one day from the oil rig out to the edge of the circular spill is 3 miles. To accomplish that task again and go another 3 miles, I would expect to need more oil. Are we in agreement with that? So that's why I fudged it and said that I need to have the amount of oil increasing. And I might be wrong. There's a calculus thing in there somewhere that I don't know. I don't think I'm wrong. Anyways, so that's that. Anyhow, this you've never seen anything like this before. So this is an example of composition and how composing functions together can be used in the world. So the first thing in part A is to write a function named R of t. And R of t is a function. It's important that we respect the names of our functions now. What does R stand for? The radius. And what is t? Good for you guys. And understand that when we talk about this, every problem like this has an initial time where t equals 0. T equals 0 is the moment that the oil started spilling. That's like day 0, if you will. So when time is 0, that's the initial go time. And R of t is a function that is the radius represented by the number of days. And I don't just want to tell you what this is. I'm going to see if you guys can come up with this. Curious. Well, let me ask you some questions. What would the radius of the oil spill be after one day? 3 miles. What would the radius of the oil spill be after 2 days? 6 miles. How about after 3 days? How about after 10 days?
So it would be like times 3.
It would be. Very good for you. So sometimes we just have to get up off our butts and write our own functions. And if we know that this is linear growth, meaning that the oil spill's radius is going up by 3 every day, then we can say that the radius of the oil spill at any time after t days is equal to 3t. And we just proved that that's a legit formula because you guys were answering all those questions. After one day, it's 3 times 1. After 2 days, it's 3 times 2, so on and so forth. Any questions about that? Okay, and this is where I think it can get a little bit, actually, maybe it's not this part. I think it's part C where you're going to maybe, I don't even know. You guys are pretty tough, but part B is pretty normal. So we're going to go off and write another function here that we're going to need for the composition, and it's A of R. What does A stand for? And it is a function of what? Yeah, area is a function of a radius, right? You know that from geometry that the area of a circle is dependent upon what its radius is. So we say that area is a function of its radius, right? So A of R quite literally means that. Anyone know off the top of their head the formula for the area of a circle? Nope, it has pi in it, though. You nailed that.
Isn't it the radius times 2 times 5?
That's the circumference. Pi times diameter or 2 radius times pi. That's called the circumference. There's a special formula for area.
2R.
You're forgetting something really important, that it's a 2-dimensional measurement. Its area is a flat surface, which means it's going to be a squared because we're dealing with length and width both. So I'm not going to sit here and torment you, but it's pi r squared. Okay. So anytime we have in a circle and we want to know the area of the circle, i.e. the amount of paint it would take to cover a surface, or in this case, looking down from above, the amount of square miles of ocean that are covered by oil spill, that 2-dimensional measurement is called area, and its formula is pi r squared. So this is where we have to compose. And I think this is the part maybe that I was the most scared of. And maybe in a minute, I'll be like, why was I scared? We have to do a composition function now, which is A of t. What does that mean? Area as a function of time, right? So far, think about what we've addressed here. We've written a formula for radius as a function of time. We've written a formula for area as a function of the radius, but we have yet to connect the dots and put the pieces together. That putting the pieces together, having them work as one, is a composition. We're composing them together. Anyone want to take a shot at what the composed function would be? How is area a function of time? Good for you. Wasn't expecting you to get that quite that quickly. I'm very impressed. Do we know that at any given time, and you don't have to, as always, please never agree with me to be polite. Would you agree that at any given time, the radius of the circle is equivalent to 3t? We agree? So how a composition is going to work is we're going to compose one by plugging one. So what we've always done, it's literally what a composition is plugging one function into another function. So in Bryn, you nailed it. We're going to take the second function, the area function, and we're going to keep it as pi something squared. But just like any composition, I'm going to feed into R the other function. And the other function in this case is I know what R is, and R is 3t. So there's an example of how to use compositions of functions to bring two sorts of easily calculatable things into one sort of larger, grandiose, calculatable thing. Having said that, I'm sorry if you're lost. Don't worry, we'll practice more. What is the cleaned up and simplified version of A of t? It needs fixed. Let's start with the red parentheses. If we take the red parentheses and we square them, just focus on that part. What do we get? We get 9 and t squared. And then just with a little bit of sort of cosmetic reparation here, we're going to make this thing come out the way it should. We're going to say that A of t, properly spoken or written, is equal to 9 pi t squared. You want to always arrange your parts and pieces so that they come out kind of the way the math gods intended. That's a pretty rad little thing we just did. And so now we can go on and answer any subsequent questions about area and radius and how much time and blah, blah, blah. So that's questions A, B, and C. In A, we write the individual piece functions, and in C, we write the composed version of the two. And I think tonight when I go home, I will find some other examples for you guys of some good real world compositions. And I'll just as a courtesy, bring those back and let you see some more. Anyways, let's press on part D. On day 5, what area will be covered by the oil spill? Very good. What a perfect way to say that. The answer is exactly what the math gods are saying in this problem is I need you to evaluate the area of time function for the time value of 5. So we're using A of t, right? Not A of r. So this is not in terms of the radius, it's in terms of the time. And we're going to put 5 in place of t. So if you put 5 right here where this green arrow is pointing, what's 5 squared? 25. So the answer is 9 pi times 25. And if someone said to you, I'd like this answer to be as accurate as possible, like nothing is going to be accurate, right? We're talking like years and years and years of expertise away from where we or I am. And that is, you have to consider things like ocean current and wind speed and all these other factors that are well beyond our comprehension. But in a perfect world, you know, if the oil just spread uniformly with no shifting from wind and ocean currents, then the area in its very perfect form would be, what's that, 225 pi square miles. It's not a particularly practical answer, so let's actually put a face to the name. So this is where we grab our calculators and actually figure out what that equals. Make sure you always use your pi button. We're going to try not to ever use that 3.14 nonsense again. If you're ever on a calculator that doesn't have a pi button, 22/7 is a pretty good approximation. It's not great, but it's better than 3.14. So 225 times pi, I am getting approximately, note that we changed the equal sign, 706 point, I don't know, What is it? Does it, nothing about rounding? Let's go with thousandths, nice and consistent. So 706.858. And again, make sure you always label appropriately. Square miles. Still good? And the follow-up question E is rather than me giving you the input and you giving me the output, I give you the output and you have to backtrack to find the input. So the question on part E is how long will it take for such and such to be achieved? So in part E, we're asked when will 5,200 square miles be covered? What are we going to do?
By night. Oh. Set it equal to 9 pi t squared.
Good. So let's just remember, I'll switch colors here for a second just to bring it back, that the function a of t is equal to, what was it, 9 pi t squared. Is that correct? Is that what we did? And so what we're going to do is rather than putting 5,200 in place of the input, we're going to put it in place of the output. So the 5,200 is actually going to go right there. Okay, we can force an output just as much as we can force an input, right? Or vice versa. So it's going to say 5,200 equals 9 pi t squared. So let's always strive for two versions of every answer. Just like what we're going to do here, we're going to go for the perfect answer, perfect world, no wind current, no nothing like that. What would the algebra gods say to do here? Divide by 9 pi. So that's going to get us down to t squared equals 5,200 divided by 9 pi. And what's the last step? Square root, right? Just math skills being put to use. So in a perfect world, we could say that the amount of time it's going to take. So like if it's like some big government action movie and some big government agent comes and says, Michael, I need you to quit beating around the bush. How many days until 5,200 square miles of ocean are covered? The character in the movie is not going to say, well, sir, it's going to be exactly the square root of 5,200 divided by 9 pi days, right? So we think about, practicality. That's not what we're looking for. It pleases the math gods and college professors and dorks like me who ask for it. But at the end of the day, I just want a dang number of days. So this is where we plug it in a calculator. So let's practice that and then we'll be done. So square root. Make sure when you type in, so I'll just show you what my calculator screen is going to look like just because I want to make sure you don't miss this. My calculator, and yours are nicer than mine. I should be using one of your nice ones, but I'm just not. So mine says square root, and then it gives me this. And if I put in 5,200, if I type it in like this, why will it be wrong? If you don't know the answer, then it's really good that we're having this conversation. I'm missing something.
Yeah.
Let me tell you what my calculator is going to do. FYI. It's going to do 5,200 divided by 9 because that's what it's programmed to do. Are we clear? And it's going to get an answer. And then what's it going to do with that answer? It's going to multiply that by pi. We sometimes have to force the order of operations, right? And what do we use whenever we want to like dork around with the order of operations? Parentheses are the powerful tool. So what I need to do, and maybe what you need to do is, I'm thinking, put the extra set of parentheses around the 9 pi. And that'll force the calculator to calculate that before it divides. That's what we need. So we're going to do the square root of 5,200 divided by extra parentheses 9 pi, close parentheses, double close parentheses. The first close was for the 9 pi. The second close is for the whole square root. And I got around 13.56 days. So time would be approximately 13.561 days. So having said all of that, what do you think? Not bad? Are you still awake? Barely hanging on. What do you think? Easy. Easy, Bucky Beaver. Not bad. Here's what we'll do. Tomorrow, I will give you practice versions of all of the things that are new. All those finding inverse ones that we started with, the word problem and this other word problem. I will just type you up more, give them to you tomorrow, and I'll try to stay a little more out of your business. Sound good? Okay, cool.
That is not the other way.
Which way?
If you take your approximate answer from, which was like 706.858 for 5 days. What, shouldn't you be able to